Hello, I am Satyabroto. Thanks for coming in my channel. As I have told in my previous video, Organic Reaction Mechanism Lecture 2, that concept of hybridization is very important to understand organic reaction mechanism. So today I am going to discuss hybridization. To get daily updates of my new video, please like, share and subscribe, and don't forget to click the bell icon. I will ask a question: why will you learn hybridization, or why concept of hybridization came? I will answer this question by discussing some facts of the simplest alkane, that is methane. So first, we know that ground state electronic configuration of carbon is 1s2, 2s2, 2px1 and 2py1. To explain from this electronic configuration, we are not able to explain the tetravalency of carbon atom, because for tetravalency of carbon atom we need 4 unpaired electron, but in from the ground state electronic configuration it is clear that we have only 2 unpaired electron. So we need to explain the tetravalency of carbon. Here we have to consider the excited state electronic configuration. In excited state electronic configuration, we are assuming that one 2s electron jumps to 2pz. Now excited electronic configuration becomes 1s2, 2s1, 2px1, 2py1 and 2pz1. So now see, we have 4 unpaired electron. 4 unpaired electron. So now this we can explain the tetravalency of carbon atom. Now we can easily explain the tetravalency of carbon atom. But in methane, so we have in methane we have 1 carbon, 4 hydrogen. So 4 hydrogen means the electronic configuration of hydrogen is 1s1. So now with this we can easily explain the tetravalency of carbon atom, but we can't explain the equivalence of 4 CH bonds in methane. What do you mean? Now you can ask a question that what do you mean by equivalency of 4 CH bonds? I mean that equivalency means all 4 CH bonds are equivalent. Their bond length are same. But if as we have 2s1, 2px1, 2py1, 2pz1. So another and we have 4 1s1. So 1s1, 1s1, 1s1. So these are the hydrogen. Okay. So one may think that there will be a bond between 2s1 and 1s1 of hydrogen, 2px1 and 1s1 of hydrogen, 2py1 1s1 of hydrogen, and 2pz 1 and 1s1 of hydrogen. So in that case, obviously it is clear that the bonding between 2s1 and 1s1 and bonding between this 2p set and 2p set and 1s1 are different. So we are not able to explain the equivalency of carbon atom. So what is the way out? So we have in here we have the concept of hybridization. So here we may think that 2s1, 2px1, 2py1, 2pz1. These 4 orbitals are hybridized. 4 orbitals are hybridized to form 4 equivalent sp3 orbitals. 4 equivalent sp3 hybridized orbital. And this is very important that now during hybridization the directional characters of the orbitals are retained. What do you mean? Why? Because here 4 sp3 hybridized orbital. here during hybridization x, y and z axis are used, and it is very important because here directional character are retained, so that is why directional characters is retained. We have strong importance about directional character because it will be known in nucleophilicity. When we will discuss nucleophilicity, then we'll understand what is the importance of directional character. So as a result, we have 4 sp3 orbitals are directed towards the corner of regular tetrahedron. So how we'll draw the sp3 hybridized orbital? See, in that case, these sp3 or hybrid orbitals is in the plane of the of the screen. Okay, and these sp3 orbitals are above the plane of the screen, and these sp3 orbitals are below the plane of the screen. Okay, and each contains 1 electron. So this is in plane, these two sp3 orbitals are in plane, this is above the plane, and this is below the plane. Okay, now in 4 sp3 hybrid orbitals are overlapped by hydrogen 1s orbitals, yielding 4 sigma bonds, and so we know sigma bonds are formed through head-on overlap of 2 orbitals. So as we have 4 sp3 orbitals, these sp3 orbitals are in plane, this is above the plane, and this is below the plane, and each contains 1 electron. Now we have 4 hydrogen. We know electrons of hydrogen resides on 1s orbital. Yes, this is methane. Now this is the hybrid orbital diagram of methane. So this is 1 sigma bond, this is 1 sigma bond, this is 1 sigma bond, this is another sigma bonds, and each bonds are equal in length and strength. Okay, so we can draw methane in flying wedge representation. So flying wedge representation is that this bond indicates it is in the plane of the screen or paper. This indicates this is bold bond. This indicates this bond is above the plane of the screen or paper, and this is below the plane of the paper or screen. And from quantum mechanical calculation, it is clear we can conclude that bond angle, this HCH bond angle is 109 degree, 109.5 degree. This HCH bond angle, and all bond angles are equal. Okay, so as 1 2s and 3 2p orbitals get hybridized to form 4 sp3 hybridized orbitals, so percentage of s character is 25% and percentage of p is 75%. While this particularly for methane, because it doesn't work for monochloromethane. In monochloromethane, they like CH3Cl. Here all bond angles are not same. I am just commenting that here hybridization terms have more p character and less s character. Okay, so just I am commenting. So sp3, it is not purely sp3, maybe as here it has more p characters, so the power of p will be more than 3, so it can be 3.1 or something like that. So yeah, here we can consider it as a concept of fractional hybridization comes. So more dramatic deviation has been observed in water, where the bond angle is in water, HO is bond angle, say here it is HOH, this bond angle is 104.5 degree. So see, the we cannot assume that like in case of all like tetravalent compound like CH4 and CH3Cl, they will follow sp3 hybridization. So there are some deviation. So why this deviation comes, this thing we'll learn later. So in our next class will be on sp2 hybridization. So thank you, and if you like my videos, please subscribe this channel. Thank you.